A person invested $6,700 for 1 year, part at 8%, part at 10%, and the remainder at 12%. The total annual income from these investments was $716. The amount of money invested at 12% was $300 more than the amount invested at 8% and 10% combined. Find the amount invested at each rate. Clearly, this is a three-variable system. There are three things that we do not know. We do not know the amount invested at 8%, 10%, or 12%. Those are going to be our three variables. So let X be the amount invested at 8%. Y will be the amount invested at 10%. And Z will be the amount invested at 12%. Each one of the sentences in this question gives us the information that we need in order to write each one of the equations. We know that the total amount invested was $6,700. So our X plus Y plus Z must have a sum of $6,700. Next, we know that X was invested at 8%. We know that Y was invested at 10%. And we know that Z was invested at 12%. And our total income from these investments was $716. The last piece comes from the last part of the question. The amount of money invested at 12% was $300 more than the amount invested at 8 and 10. Translating that into an equation, the amount invested at 12% was $300 more than the amount invested at 8% and 10% combined. Now, it's clear that this last equation is not written in the form that we would like. Because we're going to be doing elimination on one of the three variables, similar to the previous examples, we want to make sure that this is written so that X, Y, and Z are all on the same side of the equation. And that's what we're going to do. We will rewrite X and Y, we'll bring Z over, and we will move negative 300 to the other side. And we have a new version of the equation in a third variable. Now, just as we did for the non-application example, we're going to decide on a variable that we need to eliminate. We're going to choose two pairs of equations, use elimination, get rid of the variable, and drop this system down to a two-equation, two-variable system. I could notice right here that I have a positive Z, and then way down in this equation, I have a negative Z. Those two equations, the top equation and the bottom equation, become natural candidates to be added together. So let's do that. The first equation was X plus Y plus Z is 6,700. The second equation was X plus Y minus Z is negative 300. Adding straight down, I create an equation in two variables that says that 2x plus 2y is equal to 6,400. I used equation number 1 and equation number 3 from the original system to create a new equation in two variables. I now need to go back to the system and choose another pair. There are only a finite number of options available, but to try to make it as easy on myself as possible, I know that this one needs to be involved somehow. So it's either 2 and 3 are going to be used, or 2 and 1 are going to be used. And because of everything being positive in 2 and in 1, 2 and 1 become the natural choice. So we're going to choose these two to do our next elimination. So again, we have X plus Y plus Z equals 6,700. And then we have our equation with all of our rates multiplied by each one of the variable amount of investments. Clearly, I don't have any opposite coefficients just yet, but I'm going to make a little bit of a different suggestion on this one. I'm going to multiply this top equation by negative 12. That's going to create negative 12s in front of all of the investment amounts. And on the right side, negative 80,400. The reason that I chose to multiply by negative 12 is because in the second equation, I'm going to make the choice to multiply by 100. Now, those two choices might seem a little strange or contradictory, but the goal is to eliminate the variable. I need a coefficient to match. And in fact, I need the coefficient of X to do the matching. I need x to be the variable that is eliminated. If I multiply all of the terms of this equation by 100, I no longer need this equation. I can see that right here I have opposite coefficients for the z's. There's plenty of ways that I could have got there. I could have multiplied by 100 in the second equation first and then adjusted. I could have chose to divide. There's different ways you could have simplified. I could have multiplied by negative 0.12 if I really wanted to. But there's something about carrying along more decimals than I need that typically ends up being problematic. So if I multiply by 12 and 100, that wipes out all the decimals and makes it a little bit easier to do the adding. Let's add down on these two. Negative 12x and 8x is negative 4x. Negative 12y and 10y is negative 2y. These make 0. Negative 80,400 plus 71,600 is 8,800. And this will be the second equation of my new system. Combining that equation together with the other equation, 2x plus 2y equals 6,400, we're going to make a new two-variable system. And negative 4x minus 2y, negative 8,800. Adding down, we'll see that that will immediately eliminate the y variable. They are already opposite coefficients of one another, which saves me a little bit of time. 2x and negative 4x is negative 2x. 2y minus 2y is 0. And 6,400 minus 8,800, negative 2,400. Dividing by negative 2, and we get that x needs to be 1,200. This is variable number 1 in our solution. Using this, we can go back to one of these two equations and attempt to figure out what y is, because we already have z eliminated. We're going to go back into the first one. We'll say 2 times 1,200 plus 2y equals 6,400. Simple solving of this equation would give you that y is equal to 2,000. So now I have the x and the y of this particular system. The last thing that I need to calculate is the z. And in order to do that, we're going to have to go back to the beginning, because these last few steps were all about making z disappear so that you can solve the two-variable system. We're going to go back to the beginning, and we're going to highlight this equation right here. And that's the one we're going to use in order to figure out what z is. So knowing that x is 1,200 and knowing that y is 2,000, the original statement of the problem said that an extra 300 with those two together gets me to z. Careful adding tells me that z equals 3,500. If you find yourself in a time bind, you'll notice that these answers all came out fairly clean and kind of nice. There's a pretty good assumption that they are correct. It doesn't seem to be anything kind of strange happening. You didn't get one weird decimal answer with a couple of nice answers. So worst case scenario is you could probably feel pretty comfortable that this is your solution. However, knowing that your solution is the ordered triple, 1,200, 2,000, 3,500, there's nothing wrong with going back and testing those solutions should you have the time. So going back to the original equation, and again, our solution is 1,200, 2,000, 3,500. If we imagine subbing those into this first equation, is there some 6,700? It is. I know this one works because that's the one that I found the last number with. I know that one has to work. The real test is really only this one. Making sure you find 8% of 1,200 and 10% of 2,000 and 12% of 3,500 and ensuring that their sum is 716. Going back through that arithmetic can save you a lot of heartache before you think, oh, I have an answer, but really you got something that doesn't work in one or more of the equations. So take the time, if you have it at the end, to go back, check your work, make sure that your solution actually works. The best thing about solving an equation, any kind of equation, single variable, two variable, three variable, three equation. The best thing about them is that they are self-checking. You can always put your answer back in to make sure that you're doing it correctly. You went through on here 3 pages of work to get that solution, eliminating variables, rewriting 3 variable equations, organizing the system to begin with. It would be unfortunate if the mistake that you made was because of something little and then you didn't catch it before you were done.